Hey everyone, welcome to this explainer. Artificial intelligence is moving at just an absolutely blistering pace right now. And today, we're embarking on a pretty deep, frankly mind-bending conceptual shift. We are going to explore the massive transition from viewing AI as simple, one-and-done answer generators to actually understanding them as dynamic systems that continuously and autonomously improve themselves. Think about the real-world impact here. We're talking about an AI that doesn't just give you a static answer, but actually iterates, corrects, and upgrades its own logic right on the fly. It is a profound evolution in how we structure machine intelligence, and it is going to change literally everything about how we interact with technology. So let's dive right in.
We're going to start with this idea. Large language models are usually presented as answer-generating systems. We give them a question and they produce a response. But an important research direction suggested a different role. Think about what that status quo actually looks like for us right now. You ask a chatbot to write a marketing email, or maybe summarize a PDF, and it spits out a single block of text. That's answer generation, right? It's helpful, sure, but it's totally limited to its very first attempt. But what if, instead of asking an LLM to produce one final answer and just stopping there, we fundamentally change its job description? We can actually ask it to become an optimizer.
So picture this. On one hand, we have traditional answer generation. This is a straight, direct line from a problem to a single answer. It's kind of like asking an architect to draw up a blueprint, taking their very first, roughest sketch and immediately building the house. No revisions. On the other hand, we step into optimization. This is a whole different ballgame. It's an iterative loop of branching candidates, continuous evaluation, and really careful selection. Instead of just taking that first sketch, the system is basically running physics simulations on 1,000 different blueprints, finding the flaws, and drafting better and better versions. This completely highlights the vast difference between merely generating an initial output and actually running a clean, iterative process to systematically improve on it.
And that brings us to what I'd call our core theorem for today. Intelligence is not only producing answers, it is continuously improving them. This is the central thesis that's going to guide our entire explainer. Because if you think about it, true intelligence really isn't just about that first thought. Think about human intelligence. Our initial gut reaction or our first rough draft is rarely, if ever, our best work. Real intelligence is the ability to reflect, compare alternatives, learn from harsh evaluation, and strategically direct your future effort toward much more promising possibilities. And guess what? AI is now adopting that exact same iterative reflection.
Okay, so let's break down the exact mechanics of how a model actually searches through a space of possibilities rather than just firing off a single answer. Imagine the AI as a dedicated team of scientists. Step 1, generate solutions. They brainstorm multiple hypotheses. Step 2, evaluate and score. They rigorously test those ideas, and each solution is assigned a score based on its performance. Step 3, review past results. The model carefully and critically examines what worked, what failed miserably, and what specific elements might be improved. And finally, Step 4, propose next generation. It blends the best parts of the previous attempts. And then, the whole process repeats, inching closer and closer to perfection every single time.
Now here is where this gets absolutely fascinating. It's the environment where all of this is taking place. We are operating in the less formal space of natural language. Usually, traditional optimization methods, the kind that run global supply chains or complex physics engines, they depend on precisely defined mathematical functions and strict calculus gradients. But let's be real, real-world problems aren't always neat math equations. An LLM can optimize a complex business strategy, a nuanced scientific hypothesis, a creative prompt, or even a software design, all using everyday natural language. It interprets its past attempts and generates better candidates in a fluid, conversational environment. It is literally talking its way toward a better solution.
Now we hit a roadblock, the problem of the proxy, when the measured objective diverges from the real objective.
See, becoming an optimizer introduces a much deeper issue. An optimizer can only optimize what it has been explicitly told to value. If a system is asked to maximize one specific score, well, it might succeed mathematically, while the larger actual system quietly deteriorates behind the scenes. Listen to these scenarios. A prompt improves on a benchmark but becomes less reliable. It essentially learns how to cheat the test rather than master the subject. Or software becomes faster but harder to maintain. It creates a nightmare of tangled code just to shave off a single millisecond. Or maybe a business process reduces costs but increases long-term risk. Once an intelligent system becomes powerful enough to search aggressively, it will absolutely exploit whatever your evaluation process fails to represent.
And there is another big structural limitation here. The process improves outputs. It does not automatically build a stable body of knowledge. So what does that actually mean? Well, think of it like a student who perfectly memorizes the answers to a multiple-choice test, but hasn't actually learned the underlying principles of physics at all. If the questions change even slightly, the whole system collapses. A basic optimization loop remembers that candidate A scored better than candidate B, but it doesn't necessarily understand the deeper structural change that caused the improvement in the first place. It might just keep searching, endlessly generating better scores, but without ever preserving a reliable, generalized account of what has actually been learned along the way.
Which leads us to our next major concept, the energetic paradigm. Controlled allocation of limited effort across an evolving system.
In this new paradigm, we really have to recognize a hard truth. Optimization is not free. Every intelligent process operates under strict energetic constraints. It has finite resources. We're talking about limited computation power, limited time, limited experimentation opportunities, and a limited inspection capacity to actually look at every possible path. An AI doesn't have an infinite battery life, and it definitely doesn't have infinite server time. It operates on a strict budget. And managing that budget, that is the absolute key to true, sustained intelligence.
And because the AI has this strict budget, the goal changes completely. The central question is no longer merely which candidate receives the highest score. We have to shift our mindset away from mere scores and fully adopt the discipline of energetic resource management. The deeper, much more critical question becomes, where should the system invest its next unit of effort? So, what does that complex resource management actually look like in practice? Imagine the AI acting like a high-level project manager, constantly deciding where to direct its limited energy. Should it explore a new possibility, verify an existing result, repair a contradiction, preserve a valuable structure, stop pursuing a low-value path? These aren't just simple math equations anymore. These are highly complex, coordinated energy allocation decisions that literally dictate the survival and success of the entire system. The optimized object itself fundamentally changes here. A conventional optimizer seeks a better answer. It's like throwing a dart. But an energetic optimizer seeks a better trajectory. It's like launching a rocket. It's asking whether each incremental improvement actually makes the entire evolving system more coherent, more reliable, and much more capable of future learning. It is the difference between just winning a single battle and actively positioning yourself to win the entire war.
But why does seeking a better trajectory matter so much? Think of a GPS that routes you through a dangerous, unpaved alley just to save 30 seconds. It's a locally superior answer, but a terrible long-term trajectory. Locally superior answers may damage the long-term process. Shortcuts create hidden instability. Promising hypotheses may contradict validated evidence. Revisions may destroy needed structures. Energetic systems have to evaluate not just what is gained in the moment, but what is displaced, weakened, or made way more expensive down the line.
Let's summarize this massive conceptual leap. Think back to where we started. The move from simple answer generation to LLM optimization was an incredibly important step. It allowed models to finally participate in iterative search, breaking free from that one-and-done chatbot mold. But the leap from repeated candidate improvement to disciplined management is far, far larger. That is the true frontier. That is the fundamental difference between just using intelligence to optimize a single answer and using energy to govern and protect the optimization process itself.
Which brings us to the threshold of a profound unknown. I want to leave you with this thought. What happens when a model becomes capable of writing the code used to improve its own future performance? That is the frontier we are rapidly approaching right now. Thanks so much for joining me for this explainer. Until next time.